In our journey to explore the science and history of our universe, the Big Bang is the primary explanation for all of this. Many studies involve thousands of researchers who have participated in this study. The data continue to support the Big Bang as the key to explaining the creation of the universe. In this theory, dark energy plays an important role and acts as an expanding force that makes the universe grow. But as science advances, new technologies emerge, leading to the development of new concepts. It is not uncommon for long-held beliefs to be challenged and revised. Recently, Michio Kaku and others have focused on an important development: the rejection of the Big Bang theory. The discovery of 750 new galaxies by the James Webb Telescope has re-examined our understanding of the origin of the universe. These newly discovered galaxies defy expectations and reveal a universe far different and more complex than previously thought. Images taken by the James Webb Space Telescope show galaxies that deviate from previous predictions. It's smaller, lighter, and older than expected, causing consternation among scientists. These unexpected phenomena challenge the main tenets of the Big Bang theory. Traditionally, the Big Bang theory states that the universe arose from a single explosion about 14 billion years ago. However, the observed galaxies tell a different story. It looks too small and too flat, defying the predictable behavior of objects in the wider world. Furthermore, the ages and masses of these galaxies are unknown. Their existence challenges the expected timeline for the formation of galaxies within the framework of the Big Bang theory. Based on these findings, scientists are re-examining our basic understanding of the origin of the universe. The discoveries of the James Webb Telescope have opened up new avenues of exploration and raised profound questions about the nature of cosmic evolution. The James Webb Space Telescope has revealed many galaxies, questioning the accuracy of the predictions made by the Big Bang theory. According to this theory, at the beginning of the creation of the universe, all the matter, energy, and all parts of the universe were compressed into a very small, very thin space called independence. In this particular, the laws of physics, particularly those described by Einstein's equations of general relativity, indicate that there is a large amount of mass and energy in a highly compressed state, occurs if the temperature is not measured. This powerful force in the individual became the seed from which the whole world emerged. After the first explosion of independence, the universe began to expand and expand. Over the course of 13.7 billion years, global inflation, a period of rapid expansion, eliminated anomalies and adjusted the distribution of matter and energy. This expansion provided the basis for the formation of galaxies, stars, and other cosmic structures. Despite the end of the universe's expansion, the universe continued to expand at a measurable rate, as evidenced by phenomena such as the redshift of light from distant galaxies. As the universe expanded and cooled, fundamental changes occurred that led to the fusion of light elements such as hydrogen and helium through a process called nucleosynthesis. These building blocks form the basis for the formation of stars, galaxies, and more complex objects in the universe. Although the Big Bang theory is supported by strong evidence, it is important to note that it may not hold true for all of reality. One of the most important pieces of evidence supporting the Big Bang theory is the cosmic microwave background, CMB, the faint radiation that fills the universe and represents the radiation after the Big Bang. The properties of the CMB, discovered in 1965, match the predictions of the Big Bang theory, providing strong support for its validity. The observed pattern of the microwave background radiation, along with its uniform temperature distribution, provides strong evidence for the Big Bang theory. This radiation is a direct echo of the universe's origins, reflecting its hot and dense state before expansion, a major event during the Big Bang. The discovery and analysis of the CMB has confirmed the Big Bang theory as the most accurate explanation for the origin of the universe. In addition, there is a lot of evidence that supports the Big Bang theory. Observations of the redshift of the Moon from distant galaxies confirm the universe's expansion. Galaxies moving away from each other in all directions are consistent with the predictions of this theory. Additionally, the abundance of light elements such as hydrogen and helium throughout the universe is consistent with the Big Bang prediction. Astronomical studies show large-scale galaxy distributions and clustering patterns consistent with theoretical expectations. Galaxies gather in groups, clusters, and superclusters, forming complex networks around the universe. This structure has been found to support the predictions of the Big Bang theory. The role of gravity in shaping the distribution of matter and the formation of galaxies is consistent with Big Bang predictions. Clusters of galaxies and the structure of the cosmic web are strong evidence for the correctness of this theory. However, recent observations from the James Webb Space Telescope challenge some aspects of the Big Bang theory. Contrary to expectations, the galaxies observed appear smooth and well-organized, rather than chaotic and disheveled from multiple collisions and mergers, as predicted by the theory. This unexpected observation raises doubts about the commonality of galaxy mergers in the evolution of galaxies. If galaxies aren't undergoing significant mergers, it becomes difficult to explain how tiny galaxies could grow into larger ones as proposed by the Big Bang theory. Additionally, the optical illusion predicted by the expanding universe hypothesis, where objects appear smaller with increasing distance due to expansion, does not seem to align with the observations. In essence, while the Big Bang theory has garnered substantial evidence supporting its validity, new observations challenge some of its fundamental assumptions. Further research and analysis is needed to resolve these differences and refine our understanding of global evolution. Recent observations from the James Webb Space Telescope have seriously re-evaluated the validity of the Big Bang theory. Equipped with advanced infrared filters, JWST has given astronomers opportunities to study distant galaxies and understand their ages. It's a big part. The abundance of massive galaxies discovered in the short time after the Big Bang theory suggests that the evolution of the universe may not be according to the expectations of this theory. In addition, the Big Bang theory is loaded with many false predictions. The differences in many specific species, such as deuterium, helium, and lithium, question the explanatory power of this theory. Furthermore, it does not take into account observed phenomena, such as the absence of predicted perturbations in the universe's structure and known symmetries in the microwave background. Despite these fundamental contradictions, the collapse of the Big Bang theory has not received much attention. This lack of understanding can be attributed to the effect of emperor's new clothes, where established concepts are questioned and criticized. In such an environment, researchers challenging the status quo may have difficulty obtaining funding for their research. This dynamic reflects the complex relationship between scientific research, institutional support, and the sustainability of leadership models. Although the recent discoveries from JWST pose a serious challenge to the Big Bang theory, the response of the scientific community and the direction of planetary research after it remains an area of great interest and debate. Challenges from the larger scientific framework, especially in astronomy, go beyond hindering the progress of individual research efforts. They also hinder efforts to correct internal defects in the current project. In many cases, scientists find themselves leading a system that stifles dissent and stifles serious inquiry. Even if their work does not directly challenge the Big Bang theory, in the past, scientists had the opportunity to do international research as a secondary job to publish papers that deviated from mainstream theories. But even these efforts are met with rejection and scorn from the international community. As the global crisis worsens, especially in 2019, the international establishment will step up efforts to protect the Big Bang theory from being banned. Today, it is very challenging to publish important articles related to the Big Bang theory in astronomy journals. This resistance makes different theories more difficult to gain attention and control in the scientific community. As a result, the pursuit of scientific progress and the discovery of alternative explanations for the origin of the universe have been hindered. Despite these problems, there are other theories that offer different ideas about the nature and origin of the universe. One of these theories is the steady-state theory, which states that the universe exists without change and will continue to exist without a beginning. Continuous creation, a key feature of the theory of stability, states that new matter is produced to maintain the density of matter in the universe, thus explaining its observed expansion and no need for a Big Bang event. Another theory, infinite expansion, suggests that our universe is just one part of a larger multiverse, consisting of many bubbles with unique laws and physical properties. The theory states that inflation global acceleration is a continuous process in several regions of the world, leading to the creation of new bubble worlds. Furthermore, the global model proposes a model in which the world undergoes repeated cycles.